let's see what we have in store in example 2. We are told the variable w varies directly with the variable t. Okay. Got it. We also know that when w equals 7, the variable t is 2. What is the value of t when w is 12? Okay, so first of all, we are given the relationship between w and t. We know that w is equal to kt because they vary directly, which means they have a linear relationship with 0 as the initial value. We also know that when w equals 7, the variable t is 2. Oh, well that must mean k is 3.5 because 2 3.5 is 7. Okay, so now we know that w is equal to 3.5 times t. So there's our scalar. Our unit ratio is that if we have the value for t, we scale it up by 3.5, and that gives us our amount of w's. What is the value of t when w is 12? Well, when w is 12, that means we need to scale it down by 3.5. So let's go ahead and do that. Okay, and when I do 12 divided by 3.5, ooh, I get a crazy decimal, like 3.24857, blah, 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 blah. I'm going to math frac it, so I hit math, and I hit enter for the fraction part. That's 24/7. And how many times does 7 go into 24? 3. And that's 21, so there would be 3 leftovers. Okay, so what is the value of t when w is 12? Three and 3/7. Now we're told that variable q varies inversely to variable p. Okay, so this means, so varies inversely means that what? Q is equal to k divided by p. Okay, so thinking reciprocal, I mean, there's the word what? The reciprocal also has the name multiplicative inverse, and so I think, okay, when I think inverse now, I'm thinking division. Okay, so q is equal to k divided by p. We also know that when q equals 7, p is equal to 2. Oh, okay, well, scale both sides up by 2 and you get k equals 14. Okay, so that gave us information about our scaling factor. So q is equal to 14 divided by p in general. What is the value of p when q equals 12? Okay, so I want you to see why we call these proportions. Yeah? This was also a proportion. I just didn't write over 1 or divide by 1. But here, it's so obvious that these are as we are constantly solving these as a proportion, or why they got their name inversely proportional to. So it looks to me like if I scale both sides up by p, then this will say 12 p's is equal to 14. Scale up, and then scale down. P is equal to 14/12. That simplifies to 7/6, or 1 1/6. So P is 1 1/6. Got it. New example. Ooh, with data. These drop and bounce heights of a golf ball were recorded by Lehman. And I referenced the textbook down here, yes. So this is not our textbook, but still a good textbook. Here's the drop height. So holding a golf ball and dropping it at different heights. And measuring how high it bounces, right? Create a scatter plot for this data. Well, okay, you're in luck. So just so that you see, in here, in list 1, I have put the drop height, and in list 2, I have put in the bounce height. So drop height, I'm treating that like it's my explanatory variable, and bounce height, I'm treating that like it's the response variable. And now let's create a scatter plot from here. Okay, so we go second stat plot and hit enter, turn it on, and we want list 1 and list 2. And then we go zoom, statistics, enter. And there is our graph. It's looking pretty linear to me. Create a scatter plot for this data. All right, so along our horizontal is the explanatory variable, drop height. In inches. And along our vertical is the responding variable, that's the bounce height in inches. And our graph ends up looking something like, it is pretty darn linear. Rough sketch? Okay. Golf ball bounce height. Does the graph have curvature? Would this be better modeled by direct variation or inverse variation? Okay. So I think the question is, I mean, direct variation was a linear relationship, so I'm going backwards, right? Direct variation is a linear, and inverse variation has this curvature about it. As so does exponential, quadratic. They have curvature too. So here, I mean, no, not really. It's pretty linear. So I feel like it should be direct variation because it looks very linear. It doesn't look exponential, doesn't look quadratic, and now it certainly doesn't look like our new thing, which is inverse variation. So I'm thinking directly linear. Write an equation describing the relationship between the two. Okay, well, our calculator does linear models. So let's go statistics, calculate the linear regression for list 1 and list 2. And we see that it has a b value here. And that b value should be 0 for us. So our relationship, and really our initial should be 0, because if you have a drop height of 0, then it'll have a bounce height of 0. So, okay, so initial of 0. And then it seems to me like we have to find our scalar factor for the two quantities. Okay, and I noticed that this said about 89%. It's probably so. What did we say? We said bounce height is approximately, and it gave a slope of 0.89. 0.89 times the drop height. Okay, so if we look back at the data, we're really saying if we take 12 and we multiply it by 0.89, what we get is 10.68. It's a little bit on the high side, but it's data. 18 times 0.89 is 16.2. So it's rough. I would say it's probably actually a little bit lower than this, but based on this initial value being a little off. Okay, so approximately, here's our model. Say what each variable represents. B equals bounce height.